day. So what we're gonna do today? Today we have a second webinar from free webinar series about IoT product development. Just a small rewind, what we have been talking months ago about. We have been covering the life cycles and different I would say pitfalls in developing IoT products. And yeah, some of you might say, well, that was a little too abstract and more oriented to product and project managers rather than engineering teams. And
Alexander, we can't hear you.
Sorry, can you hear me now?
Now we can, yes.
Okay, sorry, there was a glitch with my microphone. Okay, welcome everyone to this second webinar from the IoT series of free webinars. My name is Alexander Lubimov. I was your host last webinar, like a month ago. And just as a small rewind to the previous session, we were talking about product and project life cycles for the IoT products, and we have been covering some tricks and problems and the peculiarities about what to do and what not to do developing such products. That was a little abstract, I must admit, for some of you, but today we're going to concentrate on a more practical topic. But I would say today's topic is one of the most challenging topics, I would say, in the IoT development, and that's do's and don'ts in the battery development products. So that's what we're gonna do. The meeting will be hosted today by CTO of EKTOS Development, Sergey Shavshin, and that's gonna be fun to get some of his knowledge in this topic. The webinar format will be that you can ask questions via the chat in the small chat window you can open when you press the chat button at the bottom of your screen. And last 15 minutes, I will be responding to those questions together with Sergey. And a small announcement also is that after the webinar, we'll be pushing out the feedback form about your takeaways and stuff. And those of you who will be providing the feedback will get EKTOS battery lifetime calculation tool as a small, tiny reward for this great feedback. All right, let's get going. Go ahead, Sergey. The stage is yours.
Okay, great. Yep. So good afternoon, everyone. And welcome to the second webinar from the IoT webinars series hosted by EKTOS. The topic of today's webinar is do's and don'ts in designing battery-powered IoT products. The agenda of the webinar is introduction of EKTOS and the speaker, myself. Why do IoT products require batteries? We'll discuss this. Then we will jump to the battery selection factors for the battery-powered IoT products. We will discuss battery life estimation process. And battery powered device design risks and their mitigation. And of course, we will do some wrap up and stuff like that. So basically, a few words about EKTOS. EKTOS is a Danish-born consultancy started by two engineers back in 2007. In Vibo, and now EKTOS is represented by roughly 110 people across 3 business areas, which are electronics development, type testing and approvals, and electronics manufacturing service. We are located in 2 countries, in Denmark and in Ukraine. In Denmark, it's Viborg, Struer, and Copenhagen, and in Ukraine, it's city of Ivano-Frankivsk, where we have electronics development and electronics manufacturing. Electronics development department is the biggest business area at the moment, with 51 engineers, and we all located here in Ukraine. As for the IoT projects, the development team has successfully accomplished roughly or more than 50 IoT projects with overall NRE budget of 35 plus million DKK. Yeah, a few words about myself. My name is Sergey Shavshin. I'm a CTO in EKTOS Electronics Development Department in Ukraine. I'm working as part of EKTOS team for the last 14 years. I am basically in charge of solving the technical challenges related to the projects we are doing for our customers, and also making the technical delivery. I have a degree in electronics engineering, and I'm also a project management professional. So that was about me. Let's start. So we have this webinar series about IoT, and this webinar is about batteries in the IoT products. And why do we associate the IoT product with the battery power? It's simply because the IoT products are often remote and thus they are battery powered. And batteries in the IoT products allow them to be grid independent. They allow to make non-intrusive installations and make the products mobile, basically. And from this aspect, we could conclude that the batteries in the IoT product are expected to last for many years. Preferably, it shall never be replaced. Also, yeah, the products could be powered from the primary battery, meaning non-rechargeable battery, or from a rechargeable battery. And also, there could be some alternative to the battery power sources like solar, wind, vibration, thermal, radio frequency, etc. So basically, what we are talking today is this is an IoT product, and there is a battery in it. So we are talking about how to make, how to integrate the battery into your product. Is it that simple to make the battery powered product? Is it just about adding a battery into existing product and that's it, and it becomes a battery powered? Yeah, not really. That's not that simple. First of all, it requires a proper design in the hardware and software to be done. It's not just adding a battery. So having a weak design could lead into the product being out of operation. Meaning, like, battery is flat, the device, the product is offline, so it doesn't perform its function. So it requires some service, and then during this time the business lose money. It also could but not could, but will lead in unexpected service costs, because often, too often batteries replacement will require a serviceman going out and replacing the battery in the product. Also, it'll put the battery costs, because the batteries cost pretty much. It will also lead to the bad user experience, because the end users will need to change the batteries. Often they will need to spend money on the batteries, and the worst situation is when you need your IoT product to work and it doesn't work because of the dead battery exactly when it needs. For some products, it could even have some legal or financial responsibility, or lead to financial responsibility, like, for example, this parking device you normally use in Denmark, and in all over the Europe. And when the battery is dead, you will get a fine. And of course, it will lead into product returns and reputation losses. So we can consider the battery power as one of the tricky problems you can come across during your development process. So how we actually select the battery for the IoT product? So further in this webinar, we will discuss only primary batteries. We will not touch the rechargeable batteries for now. So basically, there are several selection factors from a product point of view for the battery. The main factor is, of course, cost. The battery cost will influence the product cost. The battery usually, takes a major part of the product cost. Then it is battery capacity. This will define for how long the battery will last, how often it will need replacement. Its power density. This will define the battery size and the product size in the end of the day, because usually the battery takes a decent part of the product volume. So this is also very important. But then, of course, availability. Is it actually possible to go and find the battery when it's time to replace it? Is it some battery type which is available like now and will be available years from now, in 5 or 7 or 10 years? And it's a possibility of customization, the customization option, because it's sometimes possible to make a custom battery pack, and usually the custom battery packs could be a selling point. So you sell your product and you have a spare parts for it. So it's important that this custom battery pack could be produced years from now, so you can support your customers with it. Here on this diagram, you can see different batteries, battery chemistries, and then the few factors, selection factors. And it's clearly seen that, for example, this zinc carbon battery, which is getting obsolete at the moment, and it's actually its availability is yes, it gets less and less available. And at the same time, it's very cheap. It has the lowest power density, and the highly available at the moment alkaline batteries. They cost more. They have average power density. So And then we come to lithium batteries, which cost much more than, for example, alkaline and thin carbon batteries. But at the same time, they are highly customizable. They can be made in different form factors and stuff like that. They have a huge power density compared to others. So it's clearly important to find and trade off between the factors and when you implement in the battery into a product. Okay. There are some selection factors, from technical point of view. The main factor is the battery chemistry. This is basically the main parameter for the battery, which defines most of the other parameters, and including cost. We also have a temperature. It's about operating temperature range. How does the battery reacts on temperature fluctuations? How does the battery reacts on negative temperatures, which is most important from my point of view. And here on this picture, you can see, for example, how the battery capacity changed from the temperature and for different battery chemistries. You can see, for example, the alkaline battery, it's a red line here. It loses roughly half of its capacity at around +5 degrees C. At the same time, nickel metal hydride battery loses half of its capacity at around -10 degrees C. And the lithium battery will run or will almost keep its capacity down to -20 here. So this is very important to select the correct battery depending on where your product will be used and in which conditions and stuff like that. The next parameter is aging. It's about how much capacity the battery will lose over the time. It's basically a self-discharge factor. Then we have average and pulse current, which the battery could provide. For the IoT product, it's a very important parameter because we are talking about IoT here taking into assuming that it has a radio frequency technology in it, and usually the radio transmission pulse currents are 100 or even 1,000 times over the average, and it's important to have a battery which can withstand this kind of pulse currents. Here in the bottom, we have an example, for example, for the coin battery. And this is basically from the battery datasheet. It says that the battery can do up to 9 milliamp, but it can only do it like during 2 seconds, maximum 12 times per day. So this puts a limitation to your product if you use this kind of battery. Another parameter is the storage time and conditions before putting into operation. For example, how long the battery was on the shelf before it was installed into the product. So here are some examples for different battery types, and you can see, for example, the shelf time for lithium battery. It can be more than 20 years. And for nickel metal hydride, it can be as small as 3 years. So it's like a very big difference. And so it's very important to select the right battery for your product. Let's now discuss the process of estimating the battery life, taking into account factors we have just discussed. Yeah, basically the process is simple. It contains several steps. Step one is define the use case. Step two is perform theoretical calculations. Step three is practical verification, and then we get the result. And we can repeat the process. We can return from every step to step one, basically, if we are not satisfied with the expectations. So let's get into the details. Yeah, step one, define the use case. Yeah, for the IoT product, it's a very important step. It's crucial to think about the battery life when you are defining the use case. So it shall be, the use case shall be real. So the IoT product performs its function, but at the same time, it shall be minimalistic. So the product only performs the function it shall do and not everything around it. Because we are talking about battery power and we need to save the battery as much as possible. When defining the use case, we should think about how often, for example, how often the device performs its business function, how often the sensor measures, does it do some data processing, and so on, so on. We also need to think about how often the device gets online. This means how often your IoT product will send the measurements to the server. How often, how much data does it receive and transmit? Is it like 16 bytes of data, or is it 2 kilobytes of data, or whatever it is? Then operation modes. Options to enter low power mode. Is it possible, or will it be possible for the product to enter this low power mode? Interface to the outside world, the communication technology, the link budget. What is the technology? Is it like Bluetooth Low Energy? Is it Wi-Fi? Is it LTE? Is it NB-IoT? Is it Sigfox? Is it LoRa? Whatever it is. So every technology will influence the power consumption, and thus it will make a big difference for the product. And of course, is it one way or both ways communication? Is there a necessity to keep the connection to the server all the time? Meaning if the device shall be online all the time, or can it periodically wake up and send the data and be in a sleep mode most of the time? Here you can see an example for typical NB-IoT product timing diagram. So we have several modes where we have like mode 0, it's like power on and boot and network registration. Then we have mode 1, which is sleep. Then we have mode 2, it's data measurements and data transfer. And then we repeat mode 1, mode 2, and so on, so on. So let's get to the next step, which is theoretical calculations. This is where we perform, based on the previously defined operation modes, we define which hardware peripherals will be enabled in that or this mode. And of course, we should think about, how the corresponding peripherals shall be configured in the software. It's very important. Then we define the current consumption for every peripheral in every operation mode, and we define for how long it will be, it will operate during the operation cycle. Here I have some examples from the spreadsheet we use for battery theoretical calculations of the battery life. And you can see here we have like different peripherals, the power supply unit, like in display, Zigbee module, then some on-chip peripherals like the MCU core, the ADC, SPI, blah, 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 blah. And then we have two operation modes, the standby when the device is in sleep mode, and then we have operation. So we calculate, basically we take a data sheet and we make the schematic and we calculate the current consumption for every peripheral in every operation mode. Then we calculate, we sum it up and we get the total number here. And then we need to take into account battery self-discharge and due to aging, storage time and conditions, and so on. And usually these parameters are given in the data sheets. And finally, we add 25% of capacity margin on top of the calculations, just to be on the safe side. And for the defined battery capacity, we calculate the operation time from that battery. And here in this example, you can see we got 2.5 months of operation on this is on 2 coin-sized batteries. And if this calculated lifetime doesn't meet our expectations, we go back to the use case correction. Yeah, the next step in the process is creating a prototype and performing the practical verification. So for the hardware and software, we do integration, we verify every function towards current consumption, like step by step. We perform current consumption measurements for the defined operation modes, and we compare the results towards the expectations, towards what we have calculated in the spreadsheets. And if there are some deviations, we carefully study every unexpected result, because this is potentially a design bug. It's either hardware and software problem, or whatever it could be, or a design bug, overall design bug. We use statistical data analysis to get like estimated battery life based on the measurements. We perform long-term measurements on the prototype. We use different kind of battery simulators. We log the current consumption over long periods of time, and we analyze the results in the Excel spreadsheets, and we carefully study every abnormal case. And of course, it's possible that the desired battery life is not achievable, and we will need to go back in the process. Here you can see an example of the data logged. This is like a practical practical case. So in red color you can see the current consumption, and this is where the device boots. It gets it initializes the peripherals, and it gets connected to the server. Then we have a transmission, here this peaks, and then we have a sleep where we have a low current consumption. And if we have something like this, there's some abnormals or unexpected behavior, we need to study it, because potentially, as I mentioned, it could be a bug or something wrong in the design. yeah, now we come to the result. And the idea, initial idea was to have 5 years on a standard coin battery, and reality is that we got 2 years on basically a custom battery pack of a car battery size. So yeah, it was something like this here. So it's like not what we expected. Yeah, this is a joke, of course, but it could be a reality. But in fact, when we get something we can't accept, we can do several things. First is to redesign. We can try to get to find some components that consume, I mean, some hardware components that consume less current. We can, of course, add more battery, and but it, as we know, it will add like product cost, increase the product cost, and we can reconsider the use cases. What we can do, we can transmit less data, we can measure with lower frequency, we can reconsider the communication technology, because, for example, GSM requires a huge battery, and like Sigfox requires a small battery because of technology. So we will need to reconsider something. And yeah, here on this diagram, you can see how expectations and reality look. Usually, you know, everything changes on the way, and we will need to find a trade-off. And yeah, based on our experience and on the process we have just discussed, we can identify some design risks and propose some mitigation to them. Basically, the design risks are the use cases always change on the way. The selected components often consume more power than expected. Operation on low battery is always a challenge, and a battery state of charge estimation is never accurate. So let's focus on each of them. Yep. Yeah, the use case always changes on the way. It's you know, pretty often happens pretty often. So basically, the device shall perform its function more often, and the sensor shall measure not every. For example, yeah, the sensor shall measure not every hour, but every 10 minutes. And the battery shall remain the same. So of course it will influence the battery life in this case. And by the way, the device shall transmit more data, for not 16 bytes per day, but 2 kilobytes per day. And at the same time, the device shall be always online. It's because, for example, the client has found a use case where the device shall have an immediate reaction, meaning the device shall be online always, it shall never sleep, and you know, it shall accept the command from the server like immediately. So in the end of the day, we go from this simple product to this complex. That's basically a reality. Then yeah, the selected components often consume more power than expected. Yeah, we shall be skeptic here about the specifications and data sheets and application notes to the hardware components used in the design, because they usually show the absolute minimum consumption, and it's sometimes hardly reachable. And yeah, this is like when you go and buy an electrical car, as the datasheet says, it will run 400 kilometers, but you get 350 in fact, and even more, you know, in the winter time you get only 300 kilometers, but the specification still says 400 kilometers, so it's the same more or less. Yeah, we shall perform detailed current leakage assessment. Pay attention to unused peripherals in the MCU. Pay attention to pull-ups, pull-downs, resistors, and built-in pull-ups, pull-downs. Please pay attention to the efficiency of the power supply units and like all ICs which have standby mode or stuff like that, because it could consume unexpectedly high current in standby. And yeah, for the battery power device, every microamp matters. So we need to be very careful. We will of course need to study the low power modes of the MCUs in details, because normally you will have some MCU in the IoT product, right? And usually the specifications, the datasheet looks attractive, and they say it consumes like nanoamps in standby or in stop mode, but usually the lowest possible sleep mode doesn't save context and RAM, meaning RAM, and it will require some extra work to be done to make the device remember its state when it gets out of the sleep mode or stop mode. And yeah, we will need to run at a minimum possible MCU clock, because it's obvious, but sometimes it needs to be checked. It's important. It's not important for the IoT product to, in most cases, it's not important to have an immediate reaction. So basically the IoT product can run on a small MCU clock. Okay, next one is the next one is operation on a low battery, which is always challenging. Yeah, peak current consumption upon transmission on a flat battery will result in voltage drop, and the device restarts, and it starts over and over again. And if the device doesn't remember its state, if it doesn't have any non-volatile memory or whatever, it will you know create an extra problem. Then there is a high impact of negative temperatures, as we already discussed, and they influence the battery capacity a lot. So the capacity drops on the negative temperatures, and for the flat battery, it will become like a real problem. So, for example, you have a product which stands as an outdoor product, and then suddenly, when the temperature during the nighttime goes below 0 degrees C, the product restarts. And yeah, also the product will be exposed to transients in all power domains, meaning basically this low power or flat battery is abnormal operation for the product, and it shall be handled correctly. So the power supplies shall be, or different power domains shall be designed correspondingly. So the next risk is related to the battery state of charge estimation, which is from our point of view never accurate. For the battery powered product, it looks obvious that there shall be some information about the battery status, where we are, and you know, usually we are talking about the state of charge. So it's when you take your mobile phone, you can see how much you know you have left. And the typical way to evaluate the battery state of charge is to measure its voltage. but for some of the chemistries, it's almost constant within its life, and it makes impossible or hard to understand where we are. Are we at 100% of battery, or we are at last 10%? For example, here you can see how the battery voltage drops while the battery is discharging, and for example, lithium battery, it looks pretty flat, almost like all the time, and then it drops suddenly in the end. So it gets hard. It makes it hard to estimate where we are based on the battery voltage measurement. And a precise state of charge estimation requires like complex design responses. It could be some power supply units that could calculate or count used energy, like columns. So knowing how much the initial battery capacity is and knowing how much energy we have used, we can estimate the capacity left. It's also possible to estimate the state of charge based on or counting of the operation time. It's like device counts itself, how much time it's online, but this only works when device knows how much current it consumes. And also the SOC estimation deviates a lot depending on the operation mode. If you have like peak current consumptions, then the voltage can drop during these peaks, and we can wrongly estimate the SOC. So it shall be done, the measurements shall be done in particular way, in particular mode, and the peak current consumption peak currents shall be taken into account. Also for the standard batteries, even if we define this state of charge estimation model for the standard batteries, like for standard AA type battery, it will be different from vendor to vendor. And when the user changes the battery, it can estimate something incorrectly. So basically what we recommend to keep it simple and not to use state of charge estimation, but use a simple threshold, voltage threshold. And when we go over the threshold, we inform the user that it's time to change the battery. Basically, that's it. Of course, for some of the products, it's not possible, but if it's possible, we recommend to do so, to do it in this way. So use a battery voltage threshold. Yeah. So yeah, what else shall we know? Yeah, that was it about the main topic of the presentation. What else shall we know about the battery powered products? Basically, it's it's general and electrical safety considerations we shall do. This is especially important for toys and medical products, of course. Then there are some battery transportation regulations, and for example, for lithium-ion batteries, you are not allowed to transport the batteries with a SOC exceeding 30%. So it shall be handled in a proper way. And of course, approvals for the custom batteries and battery packs are on your shoulders. So if you decide to go for a custom battery or custom battery pack, you will need to take care on it. Yeah, that was it for today. And basically, let's wrap it up. Yeah, we discussed three topics. We discussed the battery selection factors, and we went through the typical battery life estimation process and how to use it. Also discussed typical design risks and possible mitigation ways. So yeah, basically we can clearly see that the battery issue or battery design, the correct battery design is or incorrect battery design can create a great impact on the project and as well as an overall business case of the IoT product when going to market. Yeah, before we go to the Q&A session, yeah, I would like also to say a few words about the next webinar, which will take place or will be hosted by EKTOS. It's on 24th of November. It's about, we will show a practical case of the NB-IoT tailored module integration with Microsoft Azure and tailored app zone. So it will be in a month from now. Yeah, and if you face any issues presented in the webinar, or you will need any support in designing the IoT product, you are welcome to get in contact with us, of course. Yep, thank you.
Thanks, Sergey. That was a pretty good and interesting journey with the battery problems. So even I can design a great product now, I can feel. Great. So let me look into the questions and just try to address some of those.
Yep.
One of the question is what is the average price of a battery? So what is your knowledge about price? I don't know, maybe per watt hour, or what can you tell?
Yeah, yeah. As mentioned before, it varies a lot on battery chemistry, and yeah, depending on the technology or radio frequency technology you use. Yeah, for example, for the NB-IoT enabled product, to be able to run for 2-3 years, the battery will cost like roughly $15 to $20 US.
Okay.
I mean, yeah, the battery pack. So that's something like that, and it varies a lot, of course, on the use case.
Yeah. What I can also add a little bit is that for the small products, like you have, like a one temperature sensor and then a small enclosure and stuff, like a really simple product, the battery cost can be comparable to the whole electronic cost. So that's how it can be estimated, so to say.
Yeah, it takes a decent, part of the BOM cost, of course. Yes, exactly.
Okay, good. There was a question addressed previously before the webinar has started about Bluetooth low energy. I know that it's not really related to the battery, but the question was how to get a PC that can connect to the several Bluetooth units at the same time. I just want to mention that it's it can be done in a multi-point bonding process. So it's just about selecting the proper Bluetooth module that can be that can consist or allow several different products to be bonded to the one Bluetooth server. So that's pretty doable, actually. Okay, more questions to Sergey and the battery. Don't see any yet.
Hi.
Hello.
Hello, my name is Emin Hasanov. I'm from Ukraine, from the Vents factory, from Boyarka, and I want to ask you also about Bluetooth technology, and exactly how do you prefer to choose technology for your projects? For example, if you need to develop some remote control for consumer electronics, do you prefer infrared remotes or radio frequency? And do you think Bluetooth low energy remotes could actually replace these old technologies?
Okay, yeah, thank you for your question. I mean, you know, you're going to make your product in, and if this webinar series is about IoT products, so we prefer to use Bluetooth, of course, in this case. So that would be a choice.
Well, I think that the biggest benefit of Bluetooth will be the flexibility. You can do a lot of stuff. You can do, you know, firmware update. You can do bidirectional data transmission and stuff like that. Where the old-fashioned IR is definitely, you know, very simple way of transferring data between remote and the unit, so to say, of some kind. But I think we you know, with the great small system on chip Bluetooth modules, price-wise, we'd probably be looking into more or less the same cost with IR plus then some processor. If you can combine, you know, the processing unit with the Bluetooth SoC, might be actually comparable to the IR, and then, you know, a little passive components around an MCU and stuff. So that would be my interpretation.
Good, thank you.
All right. Any more questions from the group? We have some.
Maybe I can ask another question.
Sure.
I want to ask you about your point of view about some system of on-chip modules, for example, from Espressif.
Yep.
Do you have any experience to use these modules in battery-powered devices? Has this product any potential to be used in battery-powered products?
Okay, good. Thank you for your question. Yeah, actually, we have some good experience with Espressif modules and SoCs. The thing is that somehow they are not designed for the battery-powered applications. They consume a huge amount of energy comparing to other vendors. And we would not recommend to use them if you are going to, you know, for the applications with BLE and Wi-Fi.